In sample spaces, we're going to look at how to find the sample space, to find the pieces, the outcomes that are in that sample space, and also the number of outcomes in the sample space. All of the possible outcomes of an experiment make up what's called the sample space. You can make an organized list to show all the possible outcomes of an experiment. A way to do that is through something called a tree diagram. So our experiment is Lucy flipping 2 quarters. So for quarter number 1, she could land on heads or tails. And then for the second quarter, the second event, she could have heads and tails with a head first, or heads and tails with a tail first. So the organized list, the sample space could be heads, 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 tails, tails and heads, and then tails, tails. You can find the number of outcomes in 2 ways. First is a tree diagram. This is an organized way to see that sample space. It branches out. Each event has its own column, like what you saw with Lucy flipping 2 tails. The fundamental counting principle is exactly that, very fundamental. It saves you lots of time. You can find the number of outcomes for 2 or more experiments by multiplying the number of outcomes for each separate experiment. So let's look at this experiment. First, you have a spinner with outcomes of A, B, and C, and then you have another spinner that can land on 1 or 2. I could use a tree diagram and show the first one lands on A, B, or C, and then that A is paired with a 1 or a 2, the B is paired with a 1 or a 2, or the C is paired with a 1 or a 2. And here is my list of possible outcomes. Here is my sample space. A1, A2, B1, B2, C1, C2. What the fundamental counting principle does is it gives you a shortcut. If you're just wanting to know the number of outcomes, you can multiply 3 times 2, it gets 6. For breakfast, Clarissa can choose from oatmeal, cornflakes, or scrambled eggs. She can drink milk, orange juice, apple juice, or hot chocolate. And so the question is, what are the possible outcomes? We will use a tree diagram to get the list of the possible outcomes. And then how many outcomes are in the sample space? We can use the fundamental counting principle to find that part. So first, for what she eats. I'm going to abbreviate for this. She can eat oatmeal, she can eat cornflakes, or she could eat scrambled eggs. So I've abbreviated that O, C, F, and S, E. With oatmeal, she can drink milk, she can drink orange juice, she can drink apple juice, or she can drink hot chocolate. With cornflakes, she can do the same thing. Milk, orange juice, apple juice, or hot chocolate. And with scrambled eggs, she can pair that with milk, orange juice, apple juice, or hot chocolate. You can imagine how crazy these tree diagrams would get if you had 8 or 9, 10, or 12 choices. But it is very helpful when you don't have a lot of choices. It helps you to make sure you don't miss something. So if I were to list the outcomes, you could go off from each of these. Oatmeal with milk, oatmeal with orange juice, oatmeal with apple juice, oatmeal with hot chocolate, cornflakes with milk, cornflakes with apple juice, and so forth. So there is my sample space. How many outcomes are there? For drink, she has 1, 2, 3 choices. So this is her drink. Actually, I said that backwards. That's what she's going to eat. There we go. Times what she can drink. 1, 2, 3, 4 choices. And she gets 12 possible outcomes. Here's some that you can practice with. Go ahead and go through practice A, where you're wanting to find the possible outcomes and how many outcomes, and then part B, where you're just trying to find out how many outcomes. Practice A. Berto flips a coin and spins the spinner at the right. What are the possible outcomes and how many outcomes are in the sample space? We use a tree diagram to get the possible outcomes. Heads and tails for the first column and then the spinner on the second column. And then match all those up. Heads 1, heads 2, heads 3, heads 4, heads 5. Tails 1, tail 2, tail 3, tails 4, and tails 5. Just like how it is in the commutative property of multiplication, it doesn't matter if I listed the spinner or the coin first, because either way you're multiplying and you're going to come out with the same number of outcomes. So how many outcomes are there? 2 times 5 is 10. That's proven because I can count in my sample space. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Practice B. A pizza shop offers thick, thin, or stuffed crust. Choices of toppings are pepperoni, cheese, hamburger, sausage, bacon, onions, bell peppers, mushrooms, and pineapple. How many different one-topping pizzas could you order? I have 3 choices for crust, 9 choices in toppings. 3 times 9 is 27 pizzas. This is how Sonic knows that it has, 6,000 different drink choices or whatever it is they have. They didn't actually mix that many drinks and keep a running list of it. They took the possible combinations, they took the outcomes for each choice and multiplied them together.